Welcome to lecture 2 of module 4. In this module, we started discussing on convection heat transfer in detail. In the last lecture, we have discussed about the dimensionless numbers, and we have discussed also the dimensional analysis on how it should be done and what kind of dimensionless groups could be obtained. And today we will continue the same thing, and here we will take up we will take up a case of dimensional analysis for natural convection or free convection. So, last lecture we discussed about application of dimensional analysis for forced convection. In this lecture we will discuss application of dimensional analysis in case of free convection, also termed as natural convection. If you remember that in the last class we discussed this dimensional analysis using Buckingham pi method. The same method we are going to apply in this case also. So, let us consider in case of natural convection or free convection, what are the total variables? The variables would be, we are applying Buckingham pi method, and the variables would be heat transfer coefficient. This is of interest to us, and this will be a function of several other variables, and we know this will be a characteristic length, it will be rho density of a fluid, mu viscosity of the fluid, Cp specific heat of the fluid, then K thermal conductivity of the fluid, and there are two more terms. One is that beta expansion coefficient of the fluid, because it is inverse of temperature, as we show that, as we know that in case of natural convection there is no flow involved. It is because of increase in temperature, the fluid gets heated up, fluid elements gets heated up, and they becomes lighter, and then they go upward, and that colder fluid will come down and take its position. So, there is another term is the beta, which is you can say that fluid coefficient of thermal expansion, beta, which is having an unit of inverse of temperature, and then we have understood that density difference is happening due to differences in temperature. So, there will be a temperature difference should be another variable, and finally, there is another variable which is called gravity, because of the buoyancy effect will come into picture in this case, and therefore, the gravity also will come into picture. So, these are the variables. So, this, as I told previously also, that identification of the variables requires expertise, requires knowledge in the said area. So, one has to maybe in a new case of new problems, one has to understand that what are the variables, what are the properties that really govern, that really define the system. That has to be understood very clearly, and then only the identifications of variables would be more or less fault free. However, if we see that total number of variables now we have listed down is, particularly this in case of heat transfer, these are the very natural convection, heat transfer, these are well known fact, and this has been studied for a long time. So, this identification of the variables are becoming much more routine kind of affairs. However, we see that total number of variables in this case are, we can find out 1, 2, 3, 4, 5, 6, 7, 8, 9. So, total number of variables in this case are 9, and already we have seen in the last class that number of fundamental dimensions So, the fundamental dimensions I will be using is 4, which is nothing but we know that m, l, theta is for time and t. These are the 4. As I told in the or rather as I discussed in the last lecture, that this fundamental dimension there can be added one more term can be added, that is called energy, and that will be say q. So, in that case the fundamental dimensions could be switched over to 5 in place of 4. However, we will discuss with 4 fundamental dimensions. Under that situation, we can have 5. So, the remaining variables. So, we have the number of dimensionless groups that we may get is 9 minus 4 is equal to 5, which will so to define the system totally for a natural convection situation. Okay. Now, this natural convection can take place in a over a hot plate. It can take place in a vertical wall, in a fluid which is adjacent to a vertical wall. It can happen there. It can happen a fluid lying on a horizontal plate. In any of the situations, it can happen. Natural convection is a very routine. It's a common phenomena. It's a routine phenomena. It is seen everywhere. Whenever see in case of earth environment, air. Okay, from the daytime, in the morning the temperature of the earth is small. When we go on increasing in the daytime, the earth temperature is gradually increasing, and so natural convection starts playing a role in that. So, that way the earth's surface can be thought of as, because the curvature, the radius of curvature is very high. So, it can be thought of for a small area, small zone, it can be thought of like a flat plate kind of things. Anyway, so we have now seen that a system of natural convection or free convection could be defined by 5 dimensionless groups. So, we have to choose now the 5 core variables for that. Total number of variables we have 9, 5 will be the dimensionless group. So, we will have core variables, number of core variables will be 4. And let us assume that this should be the core variables L, then mu, then k and beta. These are the 4 core variables. Actually, these things depends. One can change these. As I told you that it is there could be, you see that the variables, there are 3 types of variables are possible. One is that defines the geometry of the system, another is that defines the flow behavior of the system, and third one is that defines the fluid properties of the system. So, because it's related to the fluid flow. So, it depends on the fluid properties of the system. For example, if we see that L is the geometrical considerations, rho, mu, Cp, thermal conductivity, these are all property, fluid property, and in addition beta is also a fluid property. Okay. And here the other point is because there is a flow property is not that way here, is not lying here because there is no velocity here. However, so that one can take suitably, he can find out that core variables, these are the 4 core variables, so that the other variables will be adjacent to the 1 dimensionless groups. That is what we have seen. So, by changing the core variables, we may land up with a different kind of dimensionless groups, but finally, as I discussed earlier also, that coupling the different dimensionless groups as we come up with, we can finally get to the traditional well known dimensionless group forms. Okay. Now, we will list down that there should be 5 dimensionless groups. Let us assume that these are these 5 dimensional pi 1, that is say L to the power a 1, mu to the power b 1, then k to the power c 1, then beta to the power D1, and then the one core group say Cp. Along with the core group, there is one variable that is added, that is the Cp. And similarly, pi 2 will be say L to the power A2, mu to the power B2, k to the power C2, beta to the power D2, and we will have say another variable rho is being placed over here. Then pi 3 we will write say L to the power A3, mu to the power B3, k to the power C3, beta to the power D3, and we will have say delta t here. Then pi 4 we will write L to the power A4, mu to the power B4, k to the power C4, beta to the power D4, and we will put say H is that dimensionless group, H is that another variable, and then pi 5. So, we have 5 dimensionless groups. This is L to the power A4 here, A5, mu to the power B5, k to the power C5, and beta to the power D5, and then finally we will have a G over here. So, like this way we have defined the equations, the pi 1, pi 2, pi 3, pi 4, pi 5 for all this. Now, we have to see that what are the dimensions for the different variables, 9 variables that we have listed down over here. So, if we see that say in the tabular form, if we try to see it, okay, we will see that this is a variable, then this is a unit, and here it is the dimension of the same variable in dimensional form. So, first one is characteristic length. And we are defining it as L. So, it has got an unit of, we can understand this is a meter and its dimension is L. Then fluid density, it is rho. We know that kg per meter cube, and we will write as ml to the power minus 3. Some of the things already we have done in the previous problem also. And then we have fluid heat capacity, we are writing it as Cp, and this is you know that watt second per kg per degree centigrade, and it will be then L to the power 2, theta to the power minus 2, T to the power minus 1. Then fluid viscosity, and it is mu, it is kg per meter per second, its unit is like this, and we will write it at m L to the power minus 1, theta to the power minus 1. Then we have fluid thermal conductivity, we will term it at 3 K, and we know that it is watt per meter per degree centigrade, and here it would be m L theta to the power minus 3 T to the power minus 1, and then fluid coefficient of thermal expansion, we will term this as beta, and this is unit is per degree centigrade, and it will be T to the power minus 1. Then gravitational acceleration, that is G, and we know this, it is meter per second square, and it will be L theta to the power minus 2. Then we have temperature difference, we will term is a delta T, and we know that is in degree centigrade, and its unit would be T. And then finally heat transfer coefficient, termed as H, and we will write watt per meter square per degree centigrade, and here it is m theta to the power minus 3 and t to the power minus 1. So, this is what the table lists down that 9 variables with their units and their dimensions. Now, what we have to do, we have to write down the equation in the form of dimensions for the different dimensionless groups, and then we have to find out by solving, by analyzing the dimensions, we have to find out the values of all the coefficients that we have listed down. Okay. So, if we see for pi 1, it is pi 1 equals to we know that L to the power A1, then mu to the power B1, then k to the power C1, beta to the power D1 and Cp. This is pi 1, and if we now write as we have done in the previous cases, as we have written in the previous cases, if we write like this, pi 1 is a dimensionless group. So, we will write as m to the power 0, L to the power 0, theta to the power 0 and t to the power 0 should be written as according to L. So, L to the power A1, then we will write m L to the power minus 1, theta to the power minus 1 whole to the power B1, then k is m L theta to the power minus 3, t to the power minus 1 whole to the power C1, and then you have t minus 1 whole to the power D1, and finally Cp is L2 theta to the power minus 2, then t to the power minus 1. So, if we write it in this way, so simplify it, m naught L naught to the power 0 t to the power 0 would be equal to m to the power B1 plus C1 into L to the power A1 plus C1 minus B1 plus 2, then theta to the power minus B1 minus 3 C1 minus 2, then t to the power minus C1 minus D1 minus 1, like this. So, from here we can say that B1 plus C1 equals to 0, then A1 plus C1 minus B1 plus 2, that is equal to 0, then we have minus B1 minus 3 C1 minus 2 equals to 0, and then minus C1 minus D1 minus 1 equals to 0. So, these 4 equations if we solve, then we will get the values to be A1 equals to 0, A1 is coming to be 0, B1 is coming to be 1, C1 will come to be minus 1 and D1 will become again as 0. So, then if we put this, then my pi 1 is becoming, we can understand L to the power 0, mu to the power 1, k to the power minus 1, beta to the power 0 and Cp to the power 1. So, this is actually mu Cp by k, the same expression we have seen in the previous day, and we call it to be Prandtl number. So, whenever any thermal conductor heat transfer phenomena is involved and when the fluid flow is involved, Prandtl number happens to be one important parameter, because it takes care of that momentum transport as well as energy transport. So, it is a ratio of two diffusivity, momentum diffusivity to the thermal diffusivity, which is both are happening. In case of laminar flow, it is a molecular level phenomena that is happening, and in case of turbulent flow, it is assumed to be like eddy movements. In case of laminar flow, it is assumed to be the molecule movement of the molecules for this momentum transport as well as the thermal transport. This is a molecular level diffusion, whereas in case of turbulent flow, it is assumed that eddies are behaving like molecules and that movement takes place. So, actually this can be written as already we have seen, nu by alpha, which is momentum diffusivity to thermal diffusivity. So, it is the molecular level transport that is being happening, for the momentum as well as energy. Okay. Now, if we see the phi 2, so we have to get like this in the similar way, we have to get 5 variables, and we will see that how the things are coming. Most of the situations they are very known things, some of cases it may not be the known thing. So, we have to see that we have to put our experience into this and to find out that whether it will come into which is coming to a known dimensionless groups or not. Okay. So, for pi 2 it will be, we know that L to the power A 2, mu to the power B 2, k to the power C 2 and beta to the power D 2 and rho. So, we will write as m to the power 0, L to the power 0, theta to the power 0 and t to the power 0 equals to L to the power A 2, then m L to the power minus 1, theta to the power minus 1, whole to the power B 2, then m L theta to the power minus 3, t to the power minus 1, whole to the power C 2, then t to the power minus 1, whole to the power D 2, and then we have m L minus 3, that is m L minus 3 is for rho. So, what finally we get, this is equals to, we can write m to the power A B 2 plus C 2 plus 1, L to the power A 2 minus B 2 plus C 2 minus 3, then theta to the power minus B 2 minus 3 C 2, and then t to the power minus C 2 minus D 2. So, finally, we get B 2 plus C 2 plus 1 equals to 0, A 2 minus B 2 plus C 2 minus 3 equals to 0, minus B 2 minus 3 C 2 equals to 0, minus C 2 minus D 2 equals to 0. So, these are the 4 equations that we develop from this, and from the equations we find some funny results, like we get A 2 is equal to 1, B 2 is equal to minus 3 by 2, C 2 is equal to half, and D 2 is equal to minus half. So, the dimensionless group becomes like this, pi 2 is becoming like this, it is L mu to the power minus 3 by 2, k to the power half, beta to the power minus half into rho. So, if we write like this pi 2 square, this will become L square rho square k by mu cube into beta. So, I have just squared it. So, this is the expression for pi 2, and this is also a dimensionless group. I have just squared this dimensionless one. So, we will see that directly this is not a very known dimensionless group, but once we go for the other one, we will see that how things become important. So, this is pi 2, then pi 3, if we see pi 3, it is written as L to the power A 3, mu to the power B 3, C to k to the power C 3, then beta to the power D 3 and delta t. So, what we find is that m to the power 0, L to the power 0, theta to the power 0, t to the power 0, that is becoming L to the power A 3 into m L minus 1, theta to the power minus 1, whole to the power B 3, then m L theta to the power minus 3, t to the power minus 1, whole to the power C 3, then t to the power minus 1, whole to the power D 3, and then this is t. So, we get this is equal to L to the power A 3 minus B 3 plus C 3, then m to the power B 3 plus C 3, then theta to the power minus B 3 minus 3 C 3, then t to the power minus C 3 minus D 3 plus 1. So, what does it say? It says that A 3 minus B 3 plus C 3 equals to 0. It also says B 3 plus C 3 equals to 0, minus B 3 minus 3 C 3 equals to 0, and minus C 3 minus D 3 plus 1 equals to 0. So, from the 4 equations we can find out that A3 equals to 0, A3 equals to 0, then B3 equals to 0, C3 equals to 0 and D3 equals to 1. What does it say? It says that pi 3 equals to beta into delta t. So, this is another dimensionless group that beta is inverse of delta t, that is pi 3. And then if you go for pi 4, we know that it is L to the power A4, mu to the power B4, k to the power C4, beta to the power D4 and h here. So, m to the power 0, L to the power 0, theta to the power 0 and t to the power 0 is becoming equal to L to the power A4 into m L to the power minus 1, theta to the power minus 1 whole to the power B4 into m L theta to the power minus 3, t to the power minus 1 C4 and then t to the power minus 1 whole to the power D4 into now here the h is m theta to the power minus 3, t to the power minus 1. Then we get this is equal to L to the power A4 minus B4 plus C4, then m to the power B4 plus C4 plus 1, theta to the power minus B4 minus 3 C4 minus 3, t to the power minus C4 minus D4 minus 1. So, from this we can say that we can generate these expressions that A4 minus B4 plus C4 is equal to 0, B4 plus C4 plus 1 equals to 0, then we will get minus B4 minus 3C4 minus 3 equals to 0 and then minus C4 minus D4 minus 1 equals to 0. From the four equations that we develop here, we get finally the expressions like this: A4 is equal to 1, B4 equals to 0, C4 is equal to minus 1 and D4 equals to 0. Then what we get, pi 4 equals to, we can say that L to the power 1, then mu to the power 0, k to the power minus 1, then beta to the power 0 and h. What is this? This is h L yes. So, this L is small l or capital L, whatever it is. So, h L by k, this becomes h L by k. So, this h L by k is nothing but it is called Nusselt number. So, Nusselt number is, as we have told, that it is the ratio of we have discussed that L by K A divided. So, we can write that L, we have defined initially L. So, L is equal to capital L. So, L by K A by 1 by H A. We told that. So, Nusselt number is the ratio of conductive resistance to the conductive resistance to the convective resistance. Okay. So, that is already we have said. Then what can be done for pi 5? In case of pi 5, we know that it is equal to L to the power A5, then mu to the power B5, then k to the power C5, then beta to the power D5 and then g. Okay. So, this says that m to the power 0, L to the power 0, theta to the power 0 and t to the power 0 is becoming like this: L to the power A5, then m L to the power minus 1, theta to the power minus 1 whole to the power B5, then we have m L theta to the power minus 3, theta to the power minus 1 whole to the power C5, then we have t to the power minus 1 whole to the power D5 and then L theta to the power minus 2, which is the unit for dimension for G. Then what we can write, this is as L to the power A5 minus B5 plus C5 plus 1, then m to the power b5 plus c5, then we have theta to the power minus b5 minus 3c5 minus 2, and then t to the power minus c5 minus d5. So, from this we can get these relations like a5 minus b5 plus c5 plus 1 equals to 0, then b5 plus c5 equals to 0, then we have minus b5 minus 3c5 minus 2 equals to 0, and then we have minus c5 minus d5 equals to 0. So, from the 4 equations we have 4 unknowns a5, b5, c5, d5, and the values are like this: a5 equals to 1, b5 equals to 1, c5 equals to minus 1, and d5 equals to 1. So, what we finally get is pi 5 equals to L to the power 1, mu to the power 1, k to the power minus 1, beta to the power 1, and g. So, what does it say? It says that pi 5 equals to L beta mu g by k. Okay. So, from this we get another, say pi 5 is also a dimensionless quantity. So, now pi 5 and pi 2, previously we have seen that pi 2 is little unknown dimensionless variable, and pi 5 is also little unknown dimensionless variable. Now, if pi 2 and pi 5 are coupled together, so if I say that pi 6 another dimensionless variable, which is nothing but pi 2 square into pi 5, then it will give us an expression like this: L cube rho. So, pi 2 square is, already we have seen, pi 2 square will be L square rho square k by mu cube into beta, and pi 5 is L mu beta g by k. So, that means it is coming to be like this. This is equal to k cancels, beta cancels, and 1 mu cancels, it is becoming like this. So, it is becoming L cube. So, we are writing L equals to L, somewhere it is capital L I have written, somewhere it is small l. So, L is L, basically characteristic length. So, L cube g rho square by mu square, that is pi 6. Now, if we now couple again that pi 6 and into pi into say this one pi 3, if we couple them into pi 3, then we get L cube rho square g by mu square into beta into delta t. This whole expression is termed as Grashof number. So, finally, I can say that this is equal to say pi 7. So, all these things together. So, finally, the 5 pi can be now replaced by, so 5 dimensionless groups pi 1, pi 2, pi 3, pi 4 and pi 5 are or can be replaced by the 3 dimensionless groups is pi 1, then pi 4 and pi 7. So, what is pi 1? Pi 1 is, already we have seen, it is Prandtl number. What is pi 4? Pi 4 is nothing but Nusselt number. And what is pi 7? Pi 7 we have seen as the Grashof number. So, finally, our target that we can say from these that Nusselt number is a function of Grashof number and Prandtl number. Now, what is this Grashof number? Grashof number also fundamentally defined as we can see in the numerator is the buoyancy force, and in the denominator the mu is there, is called viscous force. It is the ratio of two forces, buoyancy force by so this is also we should say that that this Grashof number if we try to compare between the forced convection case and now the natural convection or free convection case, we have seen that in both the cases there are Nusselt number terms, there are Prandtl number terms, and in case of forced convection there was a term that is called Reynolds number, and here that is being replaced by another terminology that is called Grashof number. So, we can also say that Grashof number has got some kind of similarities with Reynolds number. Yes, Grashof number has got similarity with Reynolds number. When Reynolds number dictates the flow conditions, flow criteria in case of forced convection heat transfer, Grashof number says in case of free convection heat transfer, it also dictates the flow condition and flow criteria, flow behavior. So, it is basically the ratio of buoyancy force to viscous force, while Reynolds number has been the ratio of inertial force to viscous force. So, the inertial force which is basically happening or coming up due to the velocity of the fluid is being replaced by a buoyancy force which is being affected or effective due to the temperature difference or in turn due to the density difference. So, that is being happening, which is the also we are terming it to be a natural convection or free convection. So, this is the similarity that we can always view, that while going for the dimensional analysis, that two different type of cases we can have a different type of dimensionless groups. Some are common and some have some analogous behavior. Okay. So, Reynolds number and Grashof number, they are analogous in nature. Okay. Now, this is about discussing with different type of systems, and to see that, to demonstrate with the different type of system, and to see that how different dimensionless groups would be developed to characterize, to define a particular system where heat transfer is taking place. And we have seen from forced convection heat transfer situation that heat transfer coefficient, convective heat transfer coefficient particularly, which is very important parameter that dictates the amount of heat to be transferred for a system, that can be found out in terms of Nusselt number, and this Nusselt number also can be found out from an expression which is composed of few more dimensionless groups, for example, Reynolds number and Prandtl number. Also, we have seen in last class that there had been some correction terms like viscosity corrections of the fluid for different temperatures because of the variation of temperatures. Here also, in case of natural convection or free convection situations, we see that same Nusselt number to characterize or to define the value of heat transfer coefficient can be obtained from function comprising of two more dimensionless groups, which is again Prandtl number and Grashof number. Okay. Now, this forced convection, so whenever the empirical relationships are being found out, when the correlations are being found out, because as I told in the last class, the correlation, necessity of having a correlation or empirical relation is to see that some system is quite effectively, quite efficiently being represented by a set of equations for the range of parameters for which the experiments have been conducted. Actually, what happens that molecular level movements, molecular level mechanism for transport of energy is so complicated many a times, particularly in turbulent flow situation. It may not be accurately predicting the heat transfer coefficient values or the rate of heat transfer, or it may not be possible to get an expression theoretically from the total conception of the mechanism that's been going on to get an expression of H in terms or Nusselt number in terms of various other dimensionless groups. So, in that situations, what people have to do? People have to perform some experiments in lab scale or in pilot scale, and then find out the dimensionless values for those parameters defining the system. As we have seen, which other dimensionless group would be important for that particular system, they will find out the values of the dimensionless groups for different runs, and then they try to find out some functions that suitably predicts the system. And we will see that there are several such correlations, several such functions are being defined, are being suggested by various researchers, and improvements are continuously going on to give a better prediction of heat transfer coefficient values. Okay. Now, when we have to see that force convection correlations for heat transfer coefficient, we can divide. Therefore, it is needed by us to learn about the different types of correlations which are available for different types of geometries, different type of flow situations. This is very important, particularly to handle some practical problems, to handle the design problems, to get the values of heat transfer coefficient values, to get the total heat transfer values. We may have to use that different type of correlations which are being used for different type of geometries. Therefore, it's needed to learn about these correlations, to get informed about these different type of correlations, though they may not have much of scientific theoretical background for these correlations. But one thing we have seen, using dimensionless analysis from the knowledge of kind of variables available, we have seen that what would be the dimensionless groups, and we will be fortunate to see that all the different correlations which are being used are related to those kind of dimensionless groups which we have already seen. So, we can see that the forced convection correlation for heat transfer we should study like this. For heat transfer coefficient, this study can be thought of for internal flows, that means the flow is through some device, and in more commonly it is a laminar flow and terminal flows through pipelines. So, we write it laminar flow through circular duct, we can have turbulent flow through circular duct, and then we can have flow through non-circular duct. So, usually the very common way of fluid flow for which the heat transfer is involved, particularly for chemical process industries, you can see that it is a circular duct or a pipe flow or a flow through tubes that we know. So, and in many situations it is the turbulent flow which is in practice. In some cases we may have to go for a laminar flow situation. For example, when we have a heating for say viscous fluid, highly viscous fluid, that time it is the laminar flow situation that prevails. Sometime some solutions or some liquid we may have to use under laminar flow situations for heat transfer, where that high shear force may lead to some damage to the structure of the solutes present in the solution. Typically, the protein solution is one such example, because proteins are big molecules, they have big chains. So, during high shear forces, the protein molecules, their structural distortion may happen, structural breakup may take place. So, the protein may get, so it is desirable for those kind of solutions to operate in a relatively low shear stress situation, and therefore, under laminar flow situations. So, laminar flow situations is not a very common, but it is some special situations, whereas turbulent flow situation is a very common for chemical process industries, and we know that particularly through circular pipes we used to have this flow. In certain cases, we may come up with non-circular duct. Typical example is that the flow through annulus, that is also a non-circular duct. Then cell and tube heat exchanger, when there is a we will discuss things in detail. The non-circular duct, it can be that flow can be taking place through a device whose cross section is not circular, which is not a pipe or a tube. Okay, and then we have external flow. And in the external flow, we can think of having flow over a flat plate, then flow across a cylinder, then we can have flow past a sphere, and flow across bank of tubes. So, these are also very important things that happens. So, in most of the cases we can see that it is a combination of internal or external flow. Some of the things are passing through. So, when there is an exchange between two fluids, one fluid is possibly flowing through the internal flow configuration, another fluid is flowing through the external flow configuration. So, we may come up with a combination of the internal flow and external flow situations. So, under both the situations, we need to know that how would be the heat transfer coefficient values and how would be the heat transfer rates, that we may have to find out. Okay. And then there is another situation that where we should have some study and some ideas about the heat transfer coefficient is the flow through heat transfer coefficient in a packed bed or a fluidized bed. Okay. So, these are the things we will be seeing, that how the empirical correlations are available for different such configurations, and in successive lectures we will see that how these are available. So far we have discussed about that. So far we have discussed about the different types of dimensional analysis for forced convection heat transfer and for natural convection or free convection heat transfer. Now, we have seen that how to apply Buckingham-Pai theorem for different situations, and also we have seen that how even if required to group some unknown dimensionless groups to bring about a new or to bring about a known or traditional dimensional groups, and also we have seen that the importance of the different dimensionless groups, the physical significances, these things we have seen. Now, in the subsequent lectures, we will see for different type of situations, what are the different correlations available, and how through problems also we will see that how such kind of correlations should be used to evaluate the values of heat transfer coefficient or finally the amount of heat transfer. Okay. So, thank you.